Hi, everybody. Welcome to class today. We have here, it says here calculating, and this is a new word with matrices, the determinant of a square matrix. We're going to see what that is, what it's used for, and how to calculate it. Would you start by taking this system of equations here, the most generic 2x2 system of equations possible, and would you do the elimination method, just basic, elimination method, and solve for x, and it's going to be x in terms of a, b, c, d, e, and f. But would you take a minute to solve for x in terms of a, b, c, d, e, and f? So take a minute on that, please. Okay, so maybe you got, or you made progress towards it, but maybe something like this happened, where if you were going to eliminate the y, you'd multiply the top equation by d and the bottom equation through by b. That would make the coefficient of the y for both of them bd. So you have those bdy's. So when you subtract the two equations, you end up with AD minus BCX equals DE minus BF. And when you divide both sides, you get X equals DE minus BF over AD minus BC. Now, a quick question for you. When else have we seen specifically that AD minus BC appear in this course? You can type it in, or you could even unmute yourself and just say it. In the inverse, in the formula for the inverse, there was the denominator of all four of the elements of the 2x2 all were AD minus BC. And here's another time that AD minus BC appeared. So AD minus BC might be something important because it's already come up twice in two different contexts. One in finding the inverse, another time here in solving a system of equations. And here comes our first definition. Matrices, square matrices in particular, have a thing, a number associated with them, which is called the determinant. And the symbol, even though matrix usually has like brackets around it, the symbol for determinant is kind of like the absolute value. So it's kind of like putting like the absolute value around it. But it's pretty common to, if you're going to do the determinant of a matrix, to not put these square brackets here. So when we see that, that stands for the determinant of the 2x2 matrix. In this case, A, B, C, D. And on the graphing calculator, let me bring up the graphing calculator for a second. Sorry. While it's loading up, I'll just tell you that the formula for the determinant is very simply AD minus BC of a 2x2 matrix. So if I come over here and ask you, let me write down here what the formula. So the formula of the determinant of A, B, C, D, 2x2, is the product of these two minus the product of those two. That's the formula. Why it's the formula? Well, we'll talk about that, later on. But for now, here is a very famous and important formula. So would you calculate out the determinant of each of these 2 by 2 matrices? And I see people typed in 7. And is that second one, is it 5? Yes. So that's calculating out determinants. There are the answers. And just to show you that this isn't just some stuff that I'm making up just for fun, here's the graphing calculator. And if I say second matrix math, the very first thing, number 1, is debt. And now if I come here, if I have a matrix already programmed in, I could just put it in there. Instead, I'll go alpha zoom, and I'll just quickly make a 2 by 2 matrix. And I'll put in the 2, 1, 3, 5, just so you can see 2. You see this one has parentheses around it because it's like done like a computer function. But when I hit enter, yet 2, 1, 3, 4, that's not what I meant. Second, let me come back. And instead 2, 1, 3, 5. I told you the formula was 2 times 5 minus 3 times 1, and it did become 7 as expected. Now, there's a lot more to say about determinants, but for now, at least we have this thing defined. And here it is on the calculator again. So what does it mean to say that the determinant of the matrix 2, 1, 3, 5 is 7, and the determinant of 3, negative 2, 4, negative 1 is 5? And you could even have determinants that are negative. If BC is bigger than AD, you get a negative determinant. So the question is, what is that number? If it's a big number, is that good? Is that bad? What's going on? Well, the determinant is a little bit like the absolute value of, although it could be negative, so maybe that's not the best thing to say for it, but here's an example. One way of interpreting the determinant is that if you treated the 2 by 2 determinant as a transformation, and you took an entire shape, 2-dimensional shape, and you did that transformation on every single point of the shape, you would get a different shape. It would be like a distorted version of the original shape, maybe a dilation, maybe some kind of distortion of it. Well, that shape would have a different area than the original. And the determinant tells you the scale factor of how the area changes. So you can see this first example here. I ran every point of this little 1 by 1 square through the 2, 0, 0, 4 matrix. And 0, 0 stayed at 0, 0. And this square ended up becoming a rectangle, a 2 by 4 rectangle with area of 8. And the area and the determinant of 2, 0, 0, 4 is 8. 2 times 4 minus 0 times 0. Here is another matrix where I did this 1, 0, 0, 4. and I applied it to every point in this unit square, and it turned into this rectangle with a 1/4 area, and the determinant of 1004 is 4. So those are transformations that make squares into like rectangles. But a more complicated transformation, one where there's no zeros in it, it's just 2, 1, 3, 5, it ends up turning the square into this like parallelogram. And although it's not so obvious, I will tell you that the area of that parallelogram turns out to be 7. 7 times the area of the original shape, which was a square. And the determinant of this matrix, this 2, 1, 3, 5, is 2 times 5 minus 1 times 3. So that's actually one of the most fundamental definitions of what this determinant number means. But in another context, here's a system of equations. 2x plus 3y equals 10, 4x plus 6y equals 15. Can you work out the determinant? And then it's going to become something special. Anyone know why that happened? I see comments that the determinant became 0 in this case. So that's an unusual situation. Usually the determinant is not 0, but this time it was. What's so special about the system of equations that might have caused that to happen? What if you, yes, the equations, the lines that represent the equations are parallel. So this is a system of equations with no solutions. So that will happen if the determinant of the coefficient matrix is 0. That will mean that the equation either has no solutions or infinite solutions. So that's one special case of determinant. If it's 0, there's either no solutions or infinite solutions. If it's not 0, there's going to be exactly one solution. So I just wanted to give you a couple of ways to interpret determinants. Now, any square matrix has a determinant, and here's a 3x3 matrix with the numbers 2, 1, 5, 3, 2, 4, 1, -6, -1. And that thing has a determinant, which according to the calculator is -49. Forgetting about the negative for a second, what might that mean? What might be the geometric interpretation of that? If the determinant of something is 49, of a 3x3 is some number. Anyone have a geometric idea? Yes, I saw a 3D shape. What about the 3D shape? When you say becomes 49 times smaller, what becomes? Oh, because the negative? Actually, whether it's negative or positive won't matter as far as that interpretation. So it would become larger. And if you took any three-dimensional shape, for instance, a little 1x1 cube, and you ran every point of it through this 3x3 matrix as a transformation, you would get some kind of other thing. It's not going to be a cube, but it is going to be some kind of like a three-dimensional parallelogram looking thing. It's called a parallelepiped. That's not a good drawing of it, but its volume would be 49 times as big. So that's an interpretation of it. But how in the world do we calculate the determinant of a 3x3 Okay, for a 2 by 2, it's AD minus BC. That's great. But for a 3 by 3, it's a little bit complicated, and I'm going to teach you two different ways to do it. None of them are hard. It just could be a little bit tedious. So let me just refresh my memory on this for a second. Yes. So for a 3 by 3, and this first way only works for 3 by 3s, but then I'll give you a more general way that works for any square matrix. If you would copy the first two columns to the right like this. So now I have a big 3 by 5 matrix. And I am going to, remember how when we did AD minus BC, when we did the AD minus BC, the idea was there was like AD, BC. There was a diagonal with the A and D in it, and then there was another diagonal going, one diagonal with like a negative slope, one with a positive slope. Well, same thing is going to happen over here. But my diagonal is going to have 3 things in it. But I'm also going to take this second diagonal and this third one. That all is taking the place of the single diagonal AD in the 2 by 2 situation. In the BC situation, I'm also going to have 3 diagonals, one starting at the 5 like that, one starting at the 2, so we have these 6 diagonals. And what you do, I'll use red for this, you multiply together. The ones that are red, we multiply those together. So 2 times 2 times -1 is -4. And we add to that the product of these 3 numbers, which turns out to be 1 times 4 times 1, which is 4. And we add to that the product of these 3 numbers, which is 5 times 3 times -6, which is -90. And that's kind of like the AD. That's like the AD part from before, except it's more complicated because they were 3 different things. And from that, we are going to subtract with the parentheses around this. The thing that's like BC is going to be the sum of the green diagonals. So 1 times 2 times 5 is 10, and -6 times 4 times 2 is -48, and -1 times 3 times 1 is -3. So when I put these together, I get -90, minus, I'll put parentheses around this, -10, -48, -3 is -41. And when you combine those, you do indeed get -49, which is the same thing that the calculator says. So this green part is kind of like the BC from here. So in that way, it's a little bit of a generalization although this method only works for the 3x3, this crisscross method, but it's actually the best way of doing 3x3 matrices. So we currently have a nice way to do 2x2s, AD minus BC, and a way of doing 3x3s, doing this crisscross thing with the 6 different diagonals. You definitely want to be careful because there's a lot of negatives involved and easy to make some kind of error in this. Okay, that's the one we just did. And now I'm going to give you, and this is the last thing for today, I'm going to teach you why there's so many slides then. I guess we'll find out. Here is another way to do a 3x3 matrix. This way is a really good way because it can be generalized to 4x4s, 5x5s, things like that. And here's the way it works. You pick, this thing has 3 rows and 3 columns. So we actually have 6 different ways we could do this question. We pick a row or a column. In this case, I'm going to call this one expand along row 1. And the way this works is, if we want to do it by expanding along row 1, we take the first number in the first row and we write that number down. And then we say multiplied by the determinant of, and in here is going to go a 2x2 matrix. But which 2x2 matrix? Well, check this out. The 2x2 matrix will be the 4 numbers that would be left if I crossed off every number in the row and the column that the 2 is in. So the 4 remaining numbers are 2, 4, minus 6, minus 1. Now, I'm going to do the same thing now with the second element of that row, but you're going to alternate between positive and negative. So even though this is a 1, I'm going to say minus 1. So this has to be minus, at least in this case. I'll tell you there's going to be an exception coming, but we're going to alternate between adding and subtracting. So we did plus 2, but then we do minus 1. And that's going to be multiplied by a 2x2 determinant. That's going to be the numbers that remain when I cross off everything in the row and column that one's in. And now I go back to plus. We alternate between pluses and minuses, though I will tell you there is going to be a situation where sometimes we always alternate, but sometimes we start with plus instead of a minus. I'll tell you, or minus instead of a plus. I will let you know when that is in a second. So the last one, I take the number 5 multiplied by the determinant of 3, 2, 1, minus 6. So that's called expanding along row number 1. Now the 2x2s, those I do with the AD minus BC trick. So I'll do 2 times minus 1 is negative 2, minus a negative 24 becomes positive 22. And it does get confusing with the minus BC turns out to be plus because BC was negative. Then minus 1 times negative 3 minus 4 is negative 7. Plus 5 times negative 18 minus 2 is negative 20. This becomes, let me just go up here where I space, 44 plus 7 minus 100 is 51 minus 100, which is minus 49. So it got us the right answer. Now for 3x3s, it is faster, I think, to use the this crisscross method that I just shown you before. But so crisscross method is probably better for the 3x3 case. But there's going to be situations where this method is better. I'll tell you what those are coming up. But here's the one we just did. Now what I would, before we start doing it a different way now, I want to show you that it wouldn't matter. There are 3 rows and 3 columns. And you could expand along any row or any column. But there's one warning. If you're expanding along either, if the row or the column that you're expanding on, if that is even, you can still do it. We're expanding along row number 2. But when it's even, you start with negative. And then you switch to positive. So here, wait, I'm starting with, I'm going to do the 3, then the 2, then the 4, but it would be -3 plus 2 minus 4. Okay, so the reason we started with plus the first time is because I was expanding along row 1, which is an odd number. So if it's row 1, if it's an odd number, you start with a plus. I've seen in textbooks them make a chart like this. Yeah, this could work for to remind you of if I'm in this row, I start with plus, then minus. But I think you could just remember, if it's an even row or column, these signs are going to be minus, plus, minus, alternating that way. Okay, I'm going to pause and have you take a minute to complete the question and verify that you get -49 again. Okay, and you can see over here, and this was nice because I used different colors, and we ended up with -49 again. Now, since you can choose whatever row or column you want to do this with, how would you decide? Is there ever a time where it's easier to use one row over another row? I mean, here I had 6 choices. And in this case, the 6 choices were pretty equivalent to each other. But can anyone think of a situation where if you had, since you could choose any row or column that you want, when you might choose one row as, in what situation would one row be easier? And yes, Talia says, if there's a 0, if there's a 0 involved, that's one less, in this case, 2 by 2 determinant to figure out because it's going to get multiplied by 0 anyway. Oh, here I'm not going to say much about this except that you could expand along a column also. So if I use column 3, don't even have to take notes. I just want to show you that expanding along a column, in this case, it was an odd column. So I would do plus, minus, plus, and I still get -49. Forgot to mention that. So you could do columns or rows, whatever you want. I'm not going to worry about that right now. Huh. Strange. Okay. So why don't I then give a situation where there is a row or a column that has some zeros in it. Okay, so if you had a choice, which row or column would you use? And then why don't you go ahead and calculate it out? And yes, I see negative 45. That is the answer. We'd use the third column. We would do 5 times 1, 6, 2, 3, minus 0 times doesn't even matter, plus 0 times it doesn't even matter. And we get 5 times 3 minus 12. So when you see zeros, 2 zeros is really good, but any zeros is better than not having any zeros at all. I was thinking, even in a 2 by 2 matrix, where we have the AD minus BC, if you thought of this as, okay, I'm going to try to do this expand by a row method, look what would happen. You would get 2, and then if you got, let me write it twice so I can cross stuff out. So for 2, I'd have the matrix, the determinant of the matrix with a 5 in it, minus 3, the matrix with a 1 in it. Well, I never really said this, but the determinant of a matrix with a 1-by-1 matrix seems like it would be reasonable to think that is just the number itself. And you get 2 times 5 minus 3 times 1. In other words, AD minus BC. So this expansion along a row or column method is similar to what happens when you do the AD minus BC thing. Okay, well, that's what I wanted to show you. Why don't I give you a practice question? I'm going to pause the video. Okay, so when I hit enter, it does say negative 49. And that's because it's the exact same matrix that we've been working on all along. Okay, well, that wasn't very suspenseful then. Okay, well, that was the lesson for today. We will, over the next few days, the idea of determinant is going to be kind of powerful. But for now, it's just this kind of weird, tedious process of scrambling the numbers together and out comes some other number that doesn't seem particularly important. But it is going to be used in some important theorems coming up. So that's going to be the lesson for today. I posted test number 5, which you have 1 week for, and that ended with material from Friday. So today is the beginning of the material for the last test. Okay, does anyone have any questions or anything to ask or say, comments to make? Okay, in that case, I'll be seeing everybody tomorrow. I'm going to stop recording now, but then if people have questions for after the recording, that's fine also.